introduction because we're on somewhat about zero. We're okay. This is Professor Thuo from Iowa State. He is an associate professor and holds the Schaefer 2050 Challenge Professorship in the departments of material science and engineering, and also electrical and computer engineering as a courtesy appointment at Iowa State. So we're thrilled to have him here today, and thrilled to hear about your research project.
Thank you. So I'm going to take off the mask if it's okay with everyone. Sure. It's hard with my beautiful accent. It's very hard for me to project my voice. Let me close it.
Oh yeah, please.
I call it beautiful. It's a gift from my mom. So anyway, I wanted to share with you some of the work I plan to do. Some of it is ongoing, and we work on functional materials, and it's kind of interesting because we're driven by a problem. We want to solve a problem. And as Don said, I'm in Iowa State right now. And why do we do what we do? What is the challenge? The first challenge, and there are many problems that meet materials right now, but I'm just going to give you a few here that are dear and of great concern to me. One of them is microelectronics. I think we can all agree we have evolved from being Homo sapiens to Homo devices, right? Our biological name nowadays, it doesn't have electronics with it. I don't know what we're doing. We cannot even navigate our own neighborhoods without a GPS. But the interesting thing is that when you look at evolution in microelectronics, we have, in finding solutions, we've created problems. And this, I'm borrowing this from Eric, a scientist at IBM, who presented at a symposium I was, and he pointed out that once you go below 90 nanometers in your miniaturization, you start being profitable relative to space. So why do we keep getting smaller and smaller and all the way to 2 nanometers? The recent chip from IBM, why do we need to do that? It's because there is a social component to it, and people are willing to pay for high-end, more and more powerful devices, not because they are functional. Right? Our iPhone today is more powerful than the computer that sent us to the moon, yet all of us are not sending rockets to the moon. So why do we need such power? Well, there's a social dimension to it that I'm not going to get into. But in us getting into this, we've created another problem. As you get smaller and smaller, you have a problem with power, you have a problem with data, and you've converted Moore's law to Moore law, meaning as I get to smaller and smaller devices, I need more technology, I need more tools, I need more resources to analyze these devices, and I'm going to talk about that in a little bit. We also have been able to access the whole space of who we are, data. We're collecting data everywhere. But then the question is, how much can we handle, how much can we process? And then, of course, as we get these devices smaller, they're consuming too much of our power that actually we have a looming problem in 2035. Unless we have a solution, we will be making devices that we cannot power, right? And this is coming from DOE, and I'll share more details about that later. The other thing is that we, as a species, we have a need for us to survive. We are creating, as we advance in science and technology, we are creating more and more problems, pollution, climate change, and all that. And we need to collect all this data, and we need to improve the quality of life from all dimensions. And you ask yourself, what does materials have to do with this? Underlying any technology we make, most of the times, or oftentimes, we have a materials that is inspiring that. And as I was joking with Dan in the morning, I always tell students when I'm recruiting that the best way to know where you are or the history of the world, ask which material dominated, right? From Stone Age to Silicon Age, we have driven a lot of what we do. But even as we get all this beautiful technology and we integrate everything that we need to help the species and the quality of life improve, we have a problem. The supply of the materials is finite. The planet is not expanding. We have very finite resources, and that's why all these materials highlighted are critical. Critical in terms of supply, we have to supply this, and we have vulnerability to supply. So then we get away from just being in the science domain and in the social domain. Now we're getting into the business domain, right? So material science spans everything that we do. And just to give you a hint why this is so important, if you think about rare earths and what we use them for, and here I'm looking at just how we use them to support defense. Without rare earths, we don't have lasers, we don't have precision guided monitors, we don't have radars, electronic warfare. Talk about it, right? The quality of warfare degrades significantly. Yet, all these materials, we are at very big risk. All of us, right now, if you try to sell an electronic device that doesn't have a touch screen, a lot of people will not be very receptive to it. But look at where indium lies. Indium is so bad, the supply risk is so bad, the vulnerability is so high, that how are we going to maintain this drug called devices that we have created? And so our work is trying to get as much of this space as we can. Now, as one group, there is no way we can solve all this. So whatever I'm going to be sharing with you is we are catalyzing people who are smarter than us to use what we are doing to get to the next stage. And why me? Why should I be the one doing this? As you will see, it's not me, it's a team effort. But the underlying principle in the team that I put together is based on simplicity. I come from a small African village. And in that village, the way we survived is to piggyback on each other and use the resources you had to build a toy. Never did my parents buy me a single toy. I had to build it myself. And that simplicity, that ability to convert what is available, and almost guided by simple principles, allows you to build something very, very complex. But when you're beginning, there's no way you can predict that. For example, how did we build the internet? The most valuable resource we have right now. Nobody designed it. Nobody sat down and said, this is how we're going to communicate in 2020. Rather, we found a transistor. We found that we can build logic. They start talking within the same computer. Next thing we know, we're getting two machines to talk to each other, and from there, internet came to be. No one built it, no one manages it. This idea of emergence is what actually allows me to do the breadth of work that I'm going to be sharing with you. The other thing is not, as I said, the principle is good and beautiful, but it's not me. It's the network of people that we create that allows us to do that. And it's inspired by something very simple. In any business setting, and any HR manager will tell you that in any successful organization, you need to sustain this growth curve. You need people who are the agitators, who are going into the unknown world, who trigger ideas and bring things that are obvious to us that we did not see. But after that, innovators are the worst people to be business leaders, because the excitement for them is done the moment they have found the unknown. Then after that, you need people who are in the inquisition, execution, and people who build efficiency into the process. That's why science is very expensive, and industry is pushing, when you go to production, they're pushing you for efficiency. This is those people. Then of course, you need the sustainers, the stabilizers. And then if you have failed this curve properly, you will find that the organization will be very successful. I try as best as I can to recruit even student pools who can fill these gaps in my group. And to do that, there are tools available that we can use to actually evaluate when we're doing recruitment. You need to look at, do I have an agitator, a student who is really getting into the weeds, and who actually may not be trained under the traditional MSc program, but who is coming from a very different perspective. For example, when you have somebody who's coming from industry, their perspective into what you're doing is very, very different than a fresh graduate. And that also means that as a group, we need a set of skill set, and personally, for me, I need to have very, very varied skill sets that I have to keep improving. So I am, as much as the work is a work in progress, I too, as a mentor, as a scientist, I'm a work in progress, because nobody trained me to have all the skills that I need. The other thing that gives me confidence that we can solve some of these problems is because of where I'm coming from, right? My background and my experiences. We work across material classes. Here's an example of the portfolio in the group. We take a very simple process like shearing, Doppler and immersion, and out of this we can spin out all these technologies. We can get heat-free solder, which I'll be talking to you about tomorrow. We can use that to allow us to make single molecule electronics. We can actually move that to making self-assembled semiconductor materials, and actually start getting into systems like BISFETs that are the next, theoretically predicted to be the next generation of transistors we're going to be needing. And of course, the material that you're making here becomes really useful as a photocatalyst. So it is not that we are experts in photocatalysis or electronic materials, but we have an underlying principle that we can spin out all the way here. Based on what is happening on this side, to get under cooling, you need things to be mixed to remain amorphous. However, when you take the same material and you put it in solid state, of course, spinel decomposition takes over. And if you expand your thinking away from the traditional two-dimensional model, and you start realizing the relaxation space on these materials is multi-dimensional, a minimum of 4 dimensions at the very most, then you realize the 2D plot we make for free energy is actually just a snapshot of what we need to look at. And we expanded that, and with that we can be able to start inducing separation, pushing Canihelian type separations all the way to very complete demixing, and we can start using this in very complex samples like InList. I've had an experiment, so NC State will not be the experimentation space here. I have tried this paradigm at Iowa State, and we've been very successful in my own opinion. And we have generated about 86 papers. We have 12 granted patents. We have about 13 more pending. I've been able to get 8 PhD students in about 8 years, and 1 MS. I have 6 ongoing, and in the process I've generated 3 startups. All of them, this Sapotec works on is materializing heat-free solar. Seppo is on the separation, and this here was part of a visiting professorship in France. We're making fuel cells out of that. So I feel confident that although what I'm going to be sharing with you is kind of very far off, I feel confident I can do it. So the first theme of my group is polymeric materials. And I say polymeric materials and beyond because unlike the traditional polymer synthesis, we want to take this to a different level. We want to make materials that will trigger innovations in spaces that normally we don't think about when we think about polymer. And if you come back to this idea of electronics, if you look at what is happening, we have machined our way all the way to 2 nanometers, which of course is an economical and sustainable. And as I mentioned, the smaller you get it, the more you need. So we're moving from Moore's law to Moore law. As I make devices smaller, they become more complex. I need more metrology. I need more power to process that material. I need more data coming out of each of the things. I need more cycle time. I need more resource. They become expensive. That is why, right now in microelectronic manufacturing, any new entity that is trying to get in that space, it is cost prohibitive. That is why even as we try to bring electronic manufacturing back to the US, the infrastructure needed to do that is ridiculously expensive, and we have to be dependent on Foxconn and other facilities in China. Now, the other thing that comes with this is, as I mentioned, this is from the Semiconductor Research Corporation, Decadal. They put this every 10 years to tell us where the industry is going. As we have made the devices and we've been able to produce them, by 2035, we're going to get to a point where the power need is going to surpass what we're producing. And it's going to require us to either build ultra-energy efficient pathway, or we're going to hit a market-limited ability to power some of these. And to give you an example, the recent processor from NVIDIA, they're marketing right now, would take the equivalent of, as a country like Kenya, my home country, all the power they generate from greenhouse sources to power 1 server. And in Kenya, we have a lot of geothermal, so they have a lot of power they get out of that. And that's a significant proportion. About 30% of their power will go to power 1 server that is coming to the market now. So how do we solve this problem? Well, it turns out that we need to get beyond CMOS and beyond Moore's law. Because if we follow Moore's law, we're going to have a limitation. So far, we have been able to double the number of chips per device by 24 times. But the prediction we have will hit a limit at 27 unless we find a way of making electronic component out of hydrogen atoms, which is impossible. It's limited. And so we're going to have to start looking at either dynamic system. And what is interesting for me is the atoms and interfaces. We have to figure out how do we start using interfaces and single atoms as functional units. Because we do that, Moore's law has given us 24 doubling. We can get to 43 doubling by just building interfaces. And one of those interfaces, we become very good in making 2D materials. If I put two graphene sheets next to each other, oxidize one so I alter the band gap, I can make a bisphate. Theoretically, this has been predicted, but we have never been able to realize it. Why? Organizing those two sheets of graphene is a non-trivial endeavor. But the other thing, even if we do that, how do we get rid of all the stuff and all the investments we've done in this? Is there an opportunity for us to do a hybrid? And that's where I come in. I looked at this, and this is not my prediction. This was by Professor Sakar out of Harvard, who made this Jacob radar predicting where we might end up getting. And of course, biologics sit on the top because we have a very good example, our brain. And that's why there's a big buzz about neuromorphic computing and all that stuff like that. So how do we approach this? For us, we take a liquid metal and we look at this as a very good precursor. It's basically like a loaded bullet. It has all the stuff we need in there if we know how to manage it. And the science, the behavior of metals is very well known. Metals do corrode, and corrosion is a bad thing, but can we use it to make something that is really good? And if I make this not a solid metal, but I make it from a liquid metal, it means that at the interface I have plasticity. If I deplete the surface, it will reorganize itself because it wants to maintain that minimum in free energy. And therefore, I can actually bring an etchant and slowly remove metal ions and play around with thermodynamics, and I can force these metal ions to organize and be arranged in a way that allows me to make the material I want. And if I use self-assembly, then I don't need all that lithography that I talked about. I don't need all that from Moore's law to Moore law. And this is our approach. So we bring in something that etches out the oxide will reconstruct itself, and as it does that, we use an acid-base conjugate pair, so that the acid is etching, the ligand is capturing the metal atoms, and if you choose those metal atoms well, and you choose the ligands well, you can get a one-dimensional sample. If these are in solution, and then you use free energy or mixing, you can actually induce self-assembly of this material where you control the dimension of the material that is resulting from there. So the example I'm going to be showing you is we recruit a hydroxy ligand across there. So one of these bonds is dative. So I have hydrogen bonding across this plane, and then I have acetates that are interloping like this, so that I have weak London dispersive forces in between the sheets. And of course, we make this material, and we see that it forms what we want, and due to a crude solvent, there's some other things that we can do with it, so that it becomes like a beam-actuated, a beam-driven actuator. I'm not going to be talking about this, I'm going to focus on this material. So once we assemble these materials I mentioned, the next thing that we do is we can take now those ligands and very, very carefully polarize them so that we convert all those carbons. I have an acid, so I have two carbons, and convert them to graphitic material. I want to say graphitic because although we see signals for graphene, I've not gotten to a point where I can actually characterize that interface and engineer the quality of the graphene that is forming in there. But the other thing we see, if I have a graphitic carbon sitting next to a metal oxide crystallite, of course I create a huge dipole at the interface because this is a conductor, this is a semiconductor. How can those two exist? I generate induced gap states, and therefore I can alter a high bandgap material to a manageable bandgap material. And for us, we use gallium, and we can take gallium from from 4.7 EVs to about 3.2. If I put something like a rare earth, then along with interesting things that are going to happen there, and this is where we're going. We're tuning that metal atom there and changing the ligand and trying to balance how much carbon we have relative to the metal oxide crystallites, and also looking at how much we can not only manipulate electronic property, but how can we manipulate magnetic property? Can I use interfacial dipole and keystone type interaction to drive magnetic susceptibility in magnetic systems? And that's where I'm going right now. The other thing, since this is all self-assembled, I can actually then organize them into really beautiful wires, all the way from micrometers, 1.3 micrometer, all the way to 44 nanometer. I want to push this all the way to 5 nanometers. by self-assembly. And then, of course, the idea there is that if I can organize them very well in both 1 dimension and 2 dimension or 3 dimension, I can actually create functional units out of this. And this actually is a proposal we put together for DOE, because we found out, with the help from my colleagues in electrical engineering, if you make something like this that is self-assembled, actually you can start doing computation and data selection at the point of collection. So these, you can make them into sensors, and you can actually do the data filtration outside, so whatever is being transferred and transmitted is actually minimized, so you don't have to bring all the data that you don't need. So this is where we're going with this work. We have a $6 million proposal with DOE. If it gets funded, we'll be getting somewhere very well with that.
Can I ask a question?
Sure.
On the figure that you show on the figure 8, in the middle, on the right.
This
yeah,
one?
so, these right. So you showing going from CMOS planar transistor to like the FinFET and wraparound. How are these devices realized with your actual?
So this is the hypothesis. This is what we've done. This is our preliminary work.
Okay.
So this is what is in the proposal. So we have not made this. This is purely from literature. I should have put a reference in. These are just images from.
Yeah, I understand. But how do you go from where you are to?
Because these are microfluidics, right? So if I want to assemble this, I just need to pattern sacrificial layer here, and then I can create channels, and then when I'm done flowing, because we use liquids, we dissolve the metal, we push this liquid into the channels, and then they grow. Because the moment we etch, okay, maybe I missed something here. If I put a microfluidic channel, and I put my metal powder on one end, I put the solution, they etch, that concentrated solution will have this. Through higher dispersion, they will be pushed all the way to the end of the channel, and that forms the seed. From that end of the channel, now we get into the growth. They start growing, and that's when you get this. And because they are confined by the geometry of the channel, they will grow to the maximum dimensions of the channel. And that's it. So if I get a nano channel, I'll get nano ions. And so if I can organize 3-dimensional microfluidics, I can get this. And then, of course, I'm telling you about all those assemblies, but do they actually work? If I take fused metal, which has bismuth indium tin, before I polarize it, I see no interesting electronic property. It's all resistive. I polarize it, I get a diode right off. If I take ITO, I see some interesting tunnel-like behavior, and we are looking in more details on this. But then when I polarize it, it starts to behave like the fused metal analog. And we believe that this is because now the size of the atoms here do matter, but we need to investigate that a little bit better. And then we can make 3-dimensional devices, and we see, I'm not a device person, but we see very good transistor behavior. We see gating. Of course, when you look at, if you have beautiful patterns like this, you have to look at optical properties. So we see guided mode resonance out of this. And we can actually do sequential organization, or we can even do post-assembly modification, where we have one pattern, and then when that one is done, we add another layer that has a different spacing, and then we can fill the gaps. So we're making these ones for some studies. We have hypothesis on plasmonics. So I want to get a little bit more in details about this later. Because I'm believing that if we start getting concentration of light here, it will affect behavior of the adjacent beams, depending on the spacing. So this is where we're going with that. We want to make functional electronics, but from coordination polymers. Zero lithography or driven by cell assembly. Now coming back to the human theme, the human health theme, the other thing we can do is we can go to traditional polymer synthesis. And here, this was a student who was very curious, and I proposed this to them, and they were very excited. We always tell people that if you need an initiator first, but actually what we need to grow a polymer, we just need an electron. So why not just put an electron as the initiator, so that I don't have a pendant group on it. So we made free electrons, and from free electrons, we decided we can grow polymers, and the rates of which are going to be extremely high. We can grow, we can stitch together about 150 units of styrene per second. Why? Because our initiator is not diffusion limited. It can tunnel through the polymonomer solution, and we can make block polymers, because once I introduce an electron, I make a 3-electron system. I can make block polymers, which will have very interesting macromolecular assembly. The other thing I can also do, based on this idea of polymerization, we can take materials that are ubiquitous, very well known. Here I'm showing a paper. In just a minute, this work we are trying to get into these block polymers and to get different morphologies and to actually realize new materials, because I can get free radical polymerization and anionic polymerization in the same point, because I have a 3-electron chemistry. The other thing we're doing, we're using adsorbed water as a co-monomer. A lot of surface modification ignores this layer, but if you have a hydrophobic molecule, this becomes a very interesting interlayer because its structure, the property of the free water, capillary water, is very mobile. You can remove this much easily, but the water at the bottom here, you cannot remove it. It's almost like ice fishing. So how do you get to the surface of a material when this is immobile water? Because it's so hydrogen bonded to that. You can remove that chemically, but it's almost like doing a reaction on ice. If you have a hydrophobic molecule, it starts reacting and it will get bigger, so movement on the surface will be limited, and you start drilling a hole and you eventually get to the bottom. Simple hypothesis, we did that and we showed that if you control the condition very well, and we use paper here as an example, you can get very, very fine particles or very big particles, and these, as we expect, are dependent on the hydrophobicity of the molecule. This is a fluorinated molecule, this is non-fluorinated. And what we're doing with this is, after we developed this chemistry, we started working with a collaborator in Kenya, who is actually trying, who is in architecture, who is trying to get into structural materials and structures, semi-permanent structure. We take this that material, and also we can convert it into a seed lubricant. And here is we exploit the surface property, and then we can play with the surface area. And this is a project that has been very good to us. I'm getting about 110K per year on average from John Deere. And we've developed this seed lubricant, which allows us to replace talc, which is toxic to farmers. And because we have surface modification on the surface of these fibers, we can actually control how the material burns. If these materials don't ignite, the first point is higher than the cellulose. Of course, the cellulose will ignite fast and will create that. And this is another project that we are using for high temperature lubricant, because these material end up being a mixture of graphene and graphene oxide.
What dimension are you talking about with this microtubes?
The cross section here is 180 to about 250 micrometers. They're huge.
Oh, okay.
But the walls, I will show these pictures. I believe I might have SEM images later, but the walls can be anywhere from 100 micrometers to about 50 micrometers. They're huge. They're not carbon nanotubes. And this is what inspired it, a simple DAC. We saw that when we don't have the treatment, we get a lot of residue, a lot more ash, that if we make the chemical treatment on the paper, it burns better. This was counterintuitive. How would something that is surface modified burn better than something that is not? It's because of where the ignition is starting. If you start on the surface, you generate ash blocks the burning of the material underneath. But if you ignite sporadically on the inside, it's going to burn a little bit better, but it's not going to burn completely because it's burning inside out. And you can explain that using a combustion model. Oh, here are two examples. So here is an example of some of the tubes that we made. These are from paper fibers, and you can see these little particulates here are the byproducts of the chemical modifier we have used. So, and then what we're doing this work is I'm now interested in embedding other systems in the fibers so that during the burning process, I can actually convert them to semiconductor materials. These materials are conductive, but I want them to start having semiconductor behavior. That's why in the morning I was talking about fibers. I'm interested in this, and because we can control where we are degrading them, we can actually partially put different systems on a woven fabric without breaking down the fabric. The second theme is on molecular and bioelectronics, and here is, I'm going to tell this story a little bit backwards. I'm going to start with the bioelectronics, and then I'm going to tell you about the metal later. It's related to human health. one of the most interesting things as we get into electronics and understanding ourselves is neuro, right? Understanding how the brain works is very important. And on another point, and this was driven by a conversation with somebody here in the ARO office here, in the neuro program, is the vagus nerve. It's really, really critical in helping people who have epilepsy, who have PTSD, who have prosthetics, right? Because this is the main pathway to our brain. So if you can find a way of interfacing this now, we can actually feed and control what's in our brain. But the current way it's done, all neurostimulation right now, is driven by things like this. Now the problem is these gold electrodes, the so-called bioelectrodes, if you compare the modulus of that and the modulus of the tissue you're working on, it's day and night. Right? These are soft tissue. These are gold nanorods. So now the question becomes, how do you actually correct signal from something that is so delicate and also something that could easily move? How do you maintain that contact? So we decided, the best thing to deal with this is to find a way of printing electrodes directly on the brain and make it conformal. It turns out there are very many tools you can use to do that, and if you have the right material, you can actually screen print them, and you get fairly decent evolution. And we have shown in a previous paper that actually we can print solid metal on leaves, on those flowers, and actually thanks to a very annoying reviewer, I'll use that word, we have to print on a gel, right? We send this paper to Advanced Functional Material, and they say there's nothing here, this is just painting, print this screen on a softer material. So I told my student, get Jello and print the same texture there. And this is because the mechanism here is we can do self-filtration. The particles will sort themselves by size, and they will settle, and they will imprint on the gel, and they will stick. So making that pattern there allowed us now to start thinking, can we do this on brain? Can we start using this idea of metal particle printing? And if these metal particles are undercooled, if they conform to the surface that you're printing, then you can then pop them, and they will flow and really feel the texture of the system that you have. And so then the other thing we found out, this is the magnification of the rose flower, and we can actually tune the polydispersive such that it fills all these gaps, and we get really nice conformal electron. And this is what we did. We use self-filtration. The big particles stay on top of the texture. The smaller the particles, they penetrate in. So if you have really fine structures, you need a very polydispersed mixture. If you have well-defined structures, you just need a narrow polydispersed, and you can feel this is the same rose flower on an SEM. All the spaces are filled with particles. And you can get a cross-section of that, and you see actually the particles organize themselves like this. And now that we can put the particles there, then we do a chemical activation. They all turn solid, they phase change, and now we have a metal network that is imprinted on our rose. And I'll tell more details about this tomorrow. And also, of course, we put it on a brain here. We bought a cow brain, what we use in high schools, and we printed electrodes in there, and we showed that actually those electrodes are conductive and they're movable. So what I want to do going forward is to use this idea on actual biological relevant, clinical relevant areas, like in the neurostimulation. I don't have somebody who can do neuro, so I'm hoping if I get a chance to come here, I'll work with biomedical engineering to start actually printing electrodes on actual tissue and on animal samples, and really stuff that we can study in neurostimulation. On the far extreme, and continuing the theme of electronics, since I'm very interested in molecular assembly, I'm interested in single molecule electronics. How do you use a single molecule to build soft electronics? Now it turns out it's more complicated than just putting molecules on a surface. Self-assembled monomers are very well understood. However, there is some information gap in their structure that we have ignored for some time, and I'm working very in collaboration with other people and to try and uncover those, and hopefully we can now translate all this into molecular electronics. And the reason I'm interested in that is because from a structural point of view, if you have an odd or even parity in your molecule, the orientation of the terminal group should be different. And if it is different, you should expect to see different interfacial properties. And we demonstrate that using carborings. If carborings will be isostructural, but if the dipole changes even the slightest, I see a huge difference in electric current. We've taken this event file where we put things that can conform here, can flip, and once you put those molecules there, you can actually see a huge difference in the manifestation of this, the so-called ordinary effect, which means that in my design of molecular rectifier, it's going to be very much controlled by what I have there and what the structure is. The surface is also going to play a very big role, and we just submitted a paper where we're showing that the understanding the interrelationship between this and that is actually more complicated than we appreciate right now. For the interest of time, if you have any questions, just let me know. I'm trying to get myself in time. The other big theme in my lab is on metastable materials, and this again is driven by surfaces and interfaces, and this is a fundamental question. You know, one of those questions that you get that nag you and you won't leave. It was an accidental, this idea came to me by accident. I was interested in molecular electronics, and then the properties were not lining up for me. The science was not lining up for me, and it bugged me so much that it has occupied my group for a very long time now. And we have two big proposals that are pending. I am part of an SEC proposal and an ESCO proposal that are based on this idea. And my idea is very simple. If I take, for example, liquid metal again, my colleague does a lot of this, and I share it in a solution, if I choose my solution right, I should be able to make a liquid metal particle, and if I stabilize that metal particle, the oxide shell here will be anywhere between 0.7 nanometers to about 2.5 nanometers. It maxes out at 2.5. Now, if I have an alloy, I go back to the fundamental chemistry. I have gallium and indium. At time 0, these two will have stoichiometrically dictated chances of reacting with oxygen. But when you come here, we say this is gallium oxide. What happens to the indium that, by chance, statistically speaking, grabbed an oxygen atom? It turns out, if you pay attention to that oxide, you will see something very interesting. And that's what we did in 2011, and we found out that actually, if you analyze that very, very carefully, you'll see the organic layers, the stabilizers, and from the environment. Then you see your gallium-3. As you go down, you start seeing something interesting. You have gallium-1 species, you have some indium-3 species. Then you get gallium-0 and you get indium-0 on the interface. And we looked at this and we said, this does not make any sense. It's ridiculous. Why would I not have the eutectic statistically distributed there? And this became a very big problem for me because I didn't believe it. I was like, no, something is not right. But it turned out that the analysis was true. The Thuo series was telling us the truth about that underlay. And if I have a concentration gradient in the species that are sitting on this oxygen, I go back to my basic chemistry. Whenever you see a gradient in concentration, you can relate that to the gradient in pressure. If I have a gradient in pressure, I have work. So I ask myself, what is this work? Where is this work going? Where is this being manifested in the particle? And I tried to dismiss that question, it never disappeared. First, I had to first prove that actually the organization is true. So what we did is we grew this oxide thicker, and we followed the composition. And we see that if you grow the oxide very, very slowly, it gets thicker and thicker, and the composition stays as gallium oxide. However, you get to a certain temperature where you start seeing emergence of species that are actually rich in indium. And I go back to the analysis, the XPS and Thuo series analysis, and I'm like, okay, gallium is just coming out, building this layer, but then all of a sudden, I start seeing stuff that is very, very rich in indium. What is going on? Well, the oxide has become so thick that it's no longer nanoscale, it doesn't have the plasticity on nanomaterial, it's now behaving like bulk oxide, and when I start getting fractures due to thermal expansion, the material that is slowly oozing out is actually the underlayer that we had seen by XPS. So this gave me hope. But we went even further and we started now looking even at other alloys, and we pushed them a little bit. We did this with gallium. This is just a cartoon showing what is going on, where we have things that look like explosions coming out. And we went to Galveston, and with Galveston, we actually see gallium come out, gallium dominate the surface. Then we see indium. Then finally we see tin come out. They look like little flowers. And we published that paper in Undergrad, and I would like to continue this project more as an undergraduate project and explore other systems, because this is a very easy project to run, and undergraduates will have fun with it. We call it TOSI, thermal oxidative composition inversion, and the reason we call it that is because you start with gallium and indium like this, but then they flip when the material comes out.
What do you mean by undergraduate project? Can you explain?
It's something I want to recruit undergraduate research students to be running, because we already know the principle. It's just a matter of trying different types of alloy. What happens, for example, when I have a high entropy alloy, for example? Can I create a 7-layer composition? And I will show you tomorrow when I give my future research talk how the Galveston looks like. It's really interesting because it's fractals, but if you don't understand the underlying, or you don't have a good understanding of what's going on underneath, it's very hard to understand the patterns. Because you see the distribution of the second element, it follows almost like a fractal pattern. Then the third pattern follows the weakness, the tunnel that was created by the second one. It's almost like a weak line and pops up on top of that. So what happens when you have 3, 4, 5, 6, 7 component alloys? What if I play with the redox potential? What if I play with the distribution, or concentration of these species? I don't know. I feel like that's something that an undergrad student can do very well. It doesn't necessarily need to be a graduate student project. So, and all that work, what it informs me, that huge concentration gradient there means that I have an inbuilt stress in the particle. And this is where actually I started. That's what I was saying, I was telling that story backwards. And I started looking at the interface as a mass and energy dissipation horizon. Basically, this is where everything comes to die or everything gets amplified. And if I look at it that way, then I can start looking at that concentration gradient across the interface as a huge chemical potential gradient, which means from a thermodynamic point of view, the number of states I can generate here are much higher than whatever is happening in the middle. And so if that is true, then from a statistical mechanics point of view, this should be having a huge impact on that particle if I play my ratios right. And the way to play about the ratios is actually to balance between the size of this oxide relative to the size of the particle, which means just play around with the size of the particle. And then, you know, we go to classical nucleation theory. The first thing we did is to look at this, the simplest model of free energy across the liquid-solid interface, and we are looking for this concentration gradient. And forgive me, but I don't find it. I don't see anything here that captures this concentration gradient. So this sent me on a chase, and I know some people argue CP captures that. Not really, because CP is predominantly the bulk. And when you're at very low dimensions of the surface, the plasticity here does not allow you to put all the CP there. So we said if there is work there, it should lead to undercooling. And of course, we made the particles, and we found that as we make the particles smaller and smaller, they undercool very, very well. And here I'm just showing you bismuth. Melting point 62, here I'm showing you freezing at about 3. We can take this from 62 all the way to minus 50 and still have a 10 micrometer particle. And we know they are cool because when we feed them, they flow and they coalesce. Of course, the composition is all mixed up. We don't see the signs of spinoro. And even when a particle that is undercooled is sitting next to a solid particle, the surface is protecting it. So solidification here is going to be driven primarily by homogeneous nucleation and not heterogeneous nucleation. And of course, now we made those particles. This is what I'm going to be talking about tomorrow. We can print them. We can do a lot of patterning. And so what I'm interested in right now is to do things like reward printing, where we can now engineer these materials to do. Since we can do print screening, I want to get into a mass production of these for flexible electronics and actually start designing functional components out of this. We've been able to undercool even SAC 305 the solder in our phones, we can undercool that all the way to 63, which means you can fabricate your iPhone below 100 degrees centigrade, all of it, which opens new capabilities in terms of the materials we can use. And in terms of funding, I'm in very good conversation with the industry leaders in that field. I was very excited to get some of the big companies. I'll wait for them to make an announcement. I'm not going to do that. And I've been in collaboration with somebody in Berkeley now. He's at Etihad, but I'm looking for more collaborators here. The other thing, since we have these metastable materials driven by surfaces, we can start doing now interesting manufacturing, where we can start now making builds that we could not do before. And in traditional 3D printing, we either do the spalling or we do the rastering. But since we have these metals that are soft, we can start even getting packing that is non-traditional. Because they're no longer hashing, they don't have established hashing contacts, it's non-hashing, they're soft, they are flatter. So the way they pack and densify is completely different, so you will get much higher packing density than you will get with the regular granular matter. And if we can deposit, we can borrow from these monks who make these mandrels, they make beautiful, very beautiful patterns by just scratching on a tube. We can use sound waves to actually force them to organize in different orientations. We can use different surface chemistries to engineer how they relate with each other. And if we do that, we can now start developing new manufacturing methods that are not just based on high energy lasers. We can use low energy lasers. And we can also incorporate things like acoustic activators and actually focus those acoustic beams so that we create asymmetric gradients in the build. And you can imagine if I start with a full powder and I just focus my acoustic, my sound wave, I can actually pop all these undercooled particles where I want them to, and then when I'm done, I just release the powder and my build is right there. Engineering of what goes where by size will allow us actually to start engineering things like microstructure. And then we can also start mixed, solid liquid mixing. Because now I have the powder. If the powder weights a solid well and forms a very good intermetallic, I don't need to hit the melting point of the solid powder to be able to get in the field. So this is this thing here is part of the STC and that was proposed, but it's out right now. The other thing we can do, and I'm interested in this, and again, this is a low-hanging fruit, MS master students or senior undergraduate, is to incorporate these materials in different polymer matrices to start making self-healing, self-stiffening materials. So materials that will be mechanically activated and become rigid as you use them. And if they start to fail, you can use size to help them repair. So I'm interested in putting those in there. And these are expected to follow, as we showed, they're expected to follow a very simple thermodynamic relaxation curve that we publish in materials. Right? And of course, with that, if we have good undergrads in electrical engineering, we start making wearable components and things that respond to you as a person and the way the material is being used. So this is going to be another much simpler undergraduate type process. But the other thing that I really wanted to push, and this is something that came to me a while back, and we just did, some few demonstrations on it, and I want to push it a little bit further. If I have composition gradient here, and in the nanoscale, the oxide is optically transparent. But right below there, I will have a metal that is going to be refractive. So what happens if I shine a laser to this powder? Is the light just going to be refracted and come out? The answer is no. Why? There is a huge refractive index difference here, and so I expect I'll generate a ladder type wave across that interface, and because I have an Hessian constant contact, I will have that wave propagate all the way to the edge, but also it's going to be followed by a plasmonic wave, and therefore I can use both the radio, sound wave and the plasmonic activity to optically create the point of contact of those materials, and also induce convection, because wherever the light lands, you will get those atoms excited, you're going to destabilize that, you're going to change surface energy. If you start to change surface energy, you will induce convection. And so combination of those three events, I believe, will force the material to start flowing and building from a 10 micrometer particle to a much bigger particle. And we want to use this for manufacturing, and the fundamentals is on our side. And even the history, the other people have tried to use light to manipulate metal particles. So the only difference here is that our starting energy spot is different, and therefore the behavior is going to be very different. And also, due to surface plasticity, we will see different dampening of the daily weight than we can see with solid. And so this is what I was saying. I expect there to be a plasmonic event happening right at the point of contact, and I should draw this particle and get bigger and bigger. And we have preliminary data that are showing that this is likely what's going on. Finally, we need to get beyond surfaces and get to interfaces. And when I was reading literature on this in this area, you read the literature about how spinodal patterns happen, and interestingly, we talk about relaxation happening this way until you get to that point where you have a biphase system. But this did not quite quell my curiosity, because I asked myself, okay, we're just talking about interface energy exchange. What about the role of the interface? Does it have anything? Does the environment affect what you're seeing? Well, it turns out there are some theories out there. Here I'm showing the Lowengrab void model that shows that if you have a difference in the interfacial energy and you change the shape of the object you're trying to relax, you can actually dictate distribution. If I match this and this, it means therefore as these patterns are evolving, I can dictate what goes to one side. I can actually bias that diffusion from being a radial distribution, like we see in a terracotta cell, to actually a vector based on the shape of the particle. And if I also introduce stress, one of the least utilized of John Kahn's work, the Kahn-Large theory, I can actually apply mechanical stress and actually combine it with the interfacial stress and dictate what goes where. Right? This is an old paper. This is an old paper. This is very well studied. The fusion of these three, I've not seen yet. And so we took this and we said, you know, what can we do with this? And then, of course, with things like landscape inversion phase transformation theory, they start inspiring us that actually a combination of these multi-stimuli processing is going to be very critical in changing that. And that tells us that we need to start looking at a process like shearing in a multi-dimensional space. And if I just take the simple free energy curve and add one more dimension where I consider the phases, all of a sudden it looks very interesting. It's no longer a simple relaxation from high energy to low energy. I have other spaces I can go. So now I need to start thinking about that process as a landscape and asking myself, is it a single vector? Is it a multi-vector? Or can I shift the vector so that I start now going this way instead of going that way, which is what we teach in two-dimensional space. And you have to consider all the forces. And this led us to start even thinking further based on the quote that came from the NATO Director General, that we need to start thinking about how we recover materials from e-waste. And we decided to write a proposal. This is the title of my proposal to NATO. We call it REFISH, Rare Earth Fast Ionization and Selective Harvesting. And this, I'm not going to bore you with all the details of why we need to get that in the military, but the initial experiment shows us that we can actually push this mineral decomposition from the native, this is the alloy without any mechanical and thermal and chemical stimulation, to all the way you see the patterns evolving, all the way we get two-phase in the same particle. And of course, I believe these spaces you're seeing here is stuff that fell off because of differences in thermal expansion. And so where I'm going with this and what I'm hoping to push from NATO is to move away from just mechanical and chemical stimulation to start using temperature and light to actually push this separation to at least quantitative. And if we get to this space, this is going to be a process that we hope that NATO can take up. And actually, more recently, DARPA has put up a call based on this idea. So that's where that part is going to go. I don't know how much time I have. I don't have time. So I wanted to talk about my approach to teaching, and I'm very interested in scholarship and teaching. That's why we have two proposals today, one funded internally and one going out. And here I'm interested in looking at the product I make and not focusing on myself, but looking at how I can combine both changing behavior and building the knowledge of my students. And of course, this is related to information entropy. Everything is thermodynamics at the end of the day, right? So if you can manage entropy, you can do well, and this is, I can share this with you later. This is my approach to teaching. It's more cooperative. I don't like dictating the class. I try to accommodate students as I can, and as best I can. We're moving more towards demos and more practical-based methods of teaching. And I always ask my students to evaluate me. If I'm not doing a good job, they can do that anonymously. I don't have to know. They just tell me, whatever you said in this topic was not very good. You need to go back to it. And so, and to give you an example, I take graduate thermodynamics and break it down into 4. I cover everything from classical thermodynamics all the way to statistical and quantum thermodynamics. And I give them problems that are unsolved. For example, here is an example. This is assignment number 1 in one of my classes. They show up in class. After we're done with the syllabus, this is what I give them as the assignment. And I ask them to tell me, to help me calculate, for example, surface tension of these systems, or to tell me why these systems, the surfaces of these systems should be stable. You can see the flame here. How can it have a stable surface? Of course, this doesn't have a surface, but you can create one by making assumptions. This one has 2 surfaces, this one has 1 surface, and then we debate this in class, and we start getting into why surfaces and interface thermodynamics is important. I also use crystals and start talking about block waves and what happens at the edge of the crystal when the wave is propagating. And I was surprised. The class, they complained it was hard the first time I taught it. The second time they said it was even harder. But they asked me to have boot camp. Now it has happened 3 times. They come back and they tell us, you know the stuff you're talking about? We want to meet in the summer if you have time. And then we have like a week or 2 weeks or 3 weeks of pure thermal discussion. In graduate mentoring, this is my approach. I emphasize experimental when they're early, we go to communication, and then I want them to do us at the end of it. And if you come to my group, they will call me Martin, because I tell them there's no boss in the group, we are all colleagues. And the other thing I do, I'm also part of ICANX, and I invite all of you to attend these talks. I do outreach there. I'm a co-host, and we try to bring scientists from all over the world to promote this. And this is our calendar for 2012. I would love to see some of your faces here for the coming year. We just had Graphene Nobel laureate, we have 2 Nobel laureates coming here. We have a lot of other people. And that, they have been fortunately funded by these people. These are all my collaborators. Those are my former students and where they went. They have gone good places, so I might be doing something interesting. And with that, I hope I have preached to you. These are my students. That's what they did this to me. So thank you very much. And their faces are embedded in the picture, so I'm probably violating copyright, but I'm sorry. But sorry, I know it's a lot of material, but
Wow, that's great.
How big is your current research group?
I have 6 PhDs and 2 undergrads. Yeah. Oh, and you have just got 1 master student who just joined. So it's a 12-9 now.
I have a naive follow-up question to that. What's your lab look like? Is it a wet lab? Is it? I mean, there's so much going on. I'm trying to envision.
It's everything.
It's okay.
Yeah. So we have a tiny room, really tiny room that is completely dry for molecular electronics.
Okay.
And then we have another space where we do more of the metal processing. It's noisy. It's what I would call engineering.
Mm-hmm.
And then we have another space that is very chemistry-like.
Okay.
It's a one film hood and GPCs and all this kind of stuff.
So it is more or less what I was envisioning. Yeah.
Yeah.
Can I ask a couple
Sure.
technical questions? If you can go back to slide 9 or so, I think this is where you have these microfluidics and you're doing this etching and making these coordination complexes.
Mm-hmm.
And you made some comment about magnetic properties. I was wondering if you can elaborate on that.
How much can I say? Okay. Let me do general. I don't want to fight the issues. I don't want to get into much detail. So, if you think about magnetic moments, right? Every time you think about magnetic moment, you just think about the interaction between magnetic spins. However, an electron is a finite. So if I have a free electron sitting in an orbital and I apply a field, it almost costs me almost nothing to force it to be biased towards one side, right? So if I have a dipole somewhere and I apply a field, I'm going to force that dipole to align with the field. The problem with the way we look at magnetic materials, we say this is a spin, this is a spin, this is a spin, this is the interaction, okay, right? But we never think about what is happening here and what is happening here. We always, just like I said with the undercooling, we always pay attention here and we say the magnetization, JQ, okay, BT, right? That's what we say. Where is the surface of that material? It does not exist. So if I have a dipole here, this dipole is a tensor. This is a tensor. Tensor-tensor interaction, I have to worry about the dot product of those two. If this is easier for me to align than the magnetic moments themselves, then I can affect magnetization. Because for me to align these fields, I have to first address this. And that's what we're doing.
Okay, so this is more of a fundamental question, sort of how, I think you said susceptibility, so how the structure affects the susceptibility, or is there some other impact beyond you've got a different type of paramagnetism?
No, it's just paramagnetic behavior.
Okay.
We're not doing anything new. It's like the other cooling,
Okay.
right? We don't change the element. All we are doing is to make these a major factor in that. So, for example, we have seen about 1.5 enhancement in the magnetization of a material. When we make it with the same material, uranium XPS is the same.
Right.
Except we have a really low concentration of an interfacial layer that allows us to change this, and that actually forces this to start aligning before the magnet can do the job. So if I try to magnetize, for example, holmium oxide, that's the first one we did. If you take holmium oxide and you look at the magnetic properties, you will see it getting magnetized as you go to a more temperature. And by if you're using something, it doesn't matter, whatever the field you apply, you will see magnetization. We make that material and we embed an interfacial layer in the crystals. Then we see that the magnetization is about 1.5 times what you would expect for holmium oxide.
Okay.
We take that same material and we make it without that interfacial layer. It's just like holmium oxide.
Okay, yeah, I that's an interesting idea.
So the whole principle for us is, and I wish I can preach this more strongly, is every time we see a surface here, that's a tensor. If we can all see it that way, then the way we see thermodynamics is going to be very different. And we published a paper last year where we actually showed that there's a very nice correlation on the complexity, compositional complexity of that thin oxide and degree of matter cooling. And now what we're doing, the next materials we're doing is this, where we have seen this happening with the rare earths. We can tune them, basically tune their magnetization based on where they came from. And then my idea is in future I want to make those and combine them with this one, because I can arrange them based on how I etch the oxide, how I introduce stuff in the microfluidic channel, such that I can make optoelectronic components that have different composition as you go through.
Okay. Well, one other question here. You said you use microfluidics to do the patterning here.
The what?
You said you use microfluidics to do the patterning. So what resolution can you go down to with the microfluidic channels?
So right now, we're just going to, this is an optical grading, to be honest. It's not like, I just bought an optical grading.
Okay.
Slam it on a flat silicon surface and see what you get. So I have a colleague in aerospace who is an expert in microfluidics and nanofluidics. So we are now getting into actual fabrication of our own channels that have different structures, so that we can actually start getting things like this, but with 10 nanometer radius, and that's our fast target. And then the idea is, if you get it right, we can use a mask alignment and start packing them, so you start getting three-dimensional structures like this.
Okay. Thank you.
So we're trying to get into high-density chips. That's why I think electrical engineering one is enough to offer me cut the cell burnout.
I think we're eating into lunch, so there's no more questions.
Sorry, that's a problem when you a little bit established, you have too much to talk about.
Much is better than nothing.
I'm really fascinated with the oxide stuff, but I'll talk to you later. I mean, it's really fascinating.
Oh yeah,
So-
we need to discuss that a
Yeah.
little bit. Yeah. All right, thank you very much.
I don't know if there's anything in terms of,
Oh,
I think George will come in and do that.
Martin, I'll see you tomorrow for breakfast.
Yep.
We'll talk about this.
I could use a little bit of simulation, as you can see.
You see that there's a data.
Data, actual data processing.
You
is-
go